So in this problem, we're going to solve for relative velocity of an object in 2 dimensions. The problem reads, a boat can travel at a speed of 5 meters per second in still water. The captain of the boat wishes to cross a river that is 30 meters wide. If the boat is pointed directly west to cross the river, and the river runs from north to south with a speed of 3 meters per second, what is the resultant velocity of the boat? How far downstream does the boat land? And if the captain wishes to land directly across the river, so there's no north-south displacement, what angle must he steer the boat to cross the stream? So we should begin, obviously, by drawing out the problem. First thing I'm going to do is I'm going to put the river down so that we can see the orientation of it. And we know that the river flows from north to south with a speed of 3.00 meters per second. Then we know that the captain is trying to cross the river and he is pointed west, and that the boat can travel in still water at 5.00 meters per second, so we're going to put that down. And I think it's pretty clear that what's going to happen is as he crosses the river, he's also going to end up going down the stream. So now I'm just going to draw this on the side so that we can see more clearly that all we've really created is a right triangle. And if I want to solve for the resultant velocity of the boat, what it's really asking is, what is the hypotenuse of this triangle? That's going to be the result. So I'm going to use the Pythagorean Theorem, a squared plus b squared equals c squared. Now I'm just going to plug and chug. So 5.00 meters per second, the whole thing squared, plus 3.00 meters per second, again the whole thing squared, is equal to c squared. I plug it in a calculator, I take my radical, and what I'm going to find is that the resultant is 5.83 meters per second. So the speed, this is just the magnitude right now, the speed at which this boat is going to go relative to its starting point, right? So it started here. As it traveled to the left, it also traveled down, so it ended up taking this path, okay? And the speed at which it took that path was 5.83 meters per second. Now for velocity, we not only need a magnitude, but we need a direction. Okay? Every time I hear velocity, I need to make sure I include a direction. So I'm going to use this angle right here as my direction. To find that angle, I'm going to use my tangent function. Tangent of theta is going to be 3.00 meters per second divided by 5.00 meters per second. Keep in mind that the meaning of tangent is opposite over adjacent. It's a ratio. So I plug in my values. I use my inverse tan function. So I'm going to say theta is now tan negative 1 of 3 over 5. And I got rid of the meters per second. We can see that they canceled right out. So I don't need to include them in my tangent function. And what I'm going to find is the angle is 31.0 degrees. And I need to remember that I need to include more than just the angle. So in this case, we were pointed west and we rotated towards the south. So we're going to say that we went 31 degrees south of west. If we just said 31 degrees, we wouldn't know where we were measuring from or which way we were rotating. So we need to make sure to include that south of west. Okay, for the next part of the question, we want to find out how far downstream the boat lands. And so what I need to do is I need to break the problem up into an x and a y direction or an east-west, north-south direction. Okay. In my x direction, I know my velocity is 5.00 meters per second, and yes, it's west. It's not important right now. We can just deal with speed. And we know the distance it's going to go is 30 meters. So what we're going to do is we're going to find a time. And the reason that we're going to find a time is because as this boat travels in this direction and it lands over here, it's going to take the same amount of time it's going to take the same amount of time to cross the river as it is to go down the river. Okay? Time has to be the same in both directions. So time is equal to my distance divided by my speed. So 30 meters divided by 5.00 meters per second. And it's going to take 6 seconds. Now we're going to take that and we're going to go over to our y direction. And we know that the speed in the y direction is 3.00 meters per second. We don't know the distance. That's what we're trying to find. And the time is 6 seconds. So now we just go ahead and say distance is speed times time. We plug and chug, 3.00 meters per second times 6 seconds is going to be 18 meters. So as this travels across 30 meters, it ends up 18 meters downstream. Finally, the captain wants to point the boat in such a way that he goes directly across the stream. So what we have to contend with is this 3 meters per second that's pointed downstream. What we need to do is we need to cancel that out by angling the boat in such a way that we go 3.00 meters per second upstream. What that will do is these 3.00 meters per second pointed in opposite directions will cancel each other out. And the result will be that we just go directly across. So when we point this boat in some direction, what's going to happen is the direction we point is the direction the boat would be traveling in still water. That means the direction we're pointed is going to be the 5.00 meters per second. Then what we're going to do is we're going to make a little triangle where we want this y to be 3.00 meters per second. For the purpose of this problem, it doesn't matter what the x is, all right? So recognize what changed about this is now that 5.00 meters per second became the hypotenuse. And all we have to find to solve this problem is this angle. So in order to find that angle, what I'm going to use is I'm going to use my sine function. And I'm going to say that sine of theta is equal to opposite over hypotenuse, which is 3.00 meters per second, divided by 5.00 meters per second. Take my inverse sine function in order to find theta. Inverse sine of 3 over 5. What I'm going to find is that theta is 36.9 degrees, and again, 36.9 degrees isn't enough information because I could point down 36.9 degrees, I could point up 36.9 degrees, I could be measuring from north, from south, from east, from west, so I need to go ahead and I need to put in where I am measuring from. In this case, I am pointed north from the west axis. So I'm going to say 36.9 degrees north of west.